Hi folks, here we go with the last little section before the break, and this is on where functions meet, or where they intersect. So functions meet where the same x value produces the same y value on each graph. With the GDC, it's pretty easy to find where functions meet. You just use the intersect feature. So if we wanted to find where these two functions meet, let's look at first how we would do it with the GDC, because if it were paper 2, you wouldn't want to waste your time with analytic techniques. With the GDC, you use the intersect feature, which is, so intersect is second calc 5. And then it will ask you some questions. What's the first curve? What's the second curve? And what is the place that you think they meet? Or what's your guess? You need to press enter or equals for all three of those for it to actually calculate the point of intersection. Let's try it. Okay, I've got my functions in. This is not going to be exactly how it feels on your calculator because this is an emulator. But I'll go zoom 6 for standard window settings. And I can see the two graphs. I can't see the y-intercept on that parabola. If I changed my window settings, I could see more of it. But I can see that there are 2 points of intersection. So here's what I'm going to press. I'm going to press second, trace, which gets me to the calc menu. I go down and I choose intersect and press enter. And now your calculator is going to say first curve and you press enter. It's going to say second curve and you press enter. And then it'll ask you to guess. This one's a touch different. Okay. So for me, it asks, I'll go through this again, what my left and right bound are for this point of intersection. That's a little bit different. For you, you've done this solving equations before. And then it will tell you the point of intersection. So yours should pop up saying x equals 5, y equals 2. That's telling you that the point of intersection is a point 5,2, or one of the points of intersection. So I can write that down. One of them is 5,2. And you can see that there's going to be another one on the other side. So I'll go through the same process. I'll press second trace, or second calc, and go down, choose intersect. For you, again, it will say first curve, second curve, and then guess. So you'll just press enter, enter, and then go close to this other point of intersection. For me, it's a touch different. It asks about a left bound and a right bound, and it'll find that point of intersection. On either of our calculators should say -3, -6. On paper 2, that's how we would find points of intersection. Without a graphing calculator, we're still responsible, though, to be able to find points of intersection. So here are the 3 steps. We will equate the functions. We'll make them equal to each other. And that will help us find the x-coordinates where they meet. Once we've found the x-coordinates, we need to find the y-coordinates by subbing back in. So we'll do this exact question, but with analytic or non-GDC techniques. There's the question rewritten. What we're going to do is, first of all, equate functions. So I'll take the first one, which was x squared minus x minus 18, and I will set it equal to the other one, which is x minus 3. When I solve this, I'll find the x values where they meet. So let's see. I'll move that x over, so that'll give me -2x. I'll add 3 to both sides, so I'll have -15. Oh my gosh. And I moved it over because I wanted to make one side 0 because it was a quadratic. Right? That's how we solve quadratics. We make one side 0 and then we either factor or quadratic formula. Now I think this factor is real nice, so I'm going to factor it. But you could use quadratic formula. That's fine. And what we'll learn is that the numbers that zero out these brackets are 5 and -3. Those are the 2 x values of intersection. So the points of intersection are going to be at 5 something and at -3 something. Okay? And if you remember back to how we did this on the GDC, those actually were the x values of intersection. The question is, what is the y value? Now to find the y value, you just sub these points back into either this function or this function. Doesn't matter which, as long as you haven't botched something. Which one's easier to work with? I think the second one is a lot easier to work with. If I take this one, y equals x minus 3, and I put in a 5, let's see, because that's one of the x values of intersection. 5 minus 3, hey-o, that gives us a 2 for my y value. If, by the same token, I took that equation and put in a negative 3 into it, I would have negative 3 minus 3, or negative 6, meaning this point of intersection should be negative 3, negative 6. Let me rewrite those a little more nicely. Let's check out whether those were the same points of intersection we found before. Oh my gosh, they are. So again, the technique was equate the functions, solve for the x-coordinate, and then make sure you go back and find the y-coordinates as well. Because if they're asking you for points of intersection, and all you write is x values, then you haven't found the points of intersection. So now that you've seen the technique, maybe you want to take a look at this one, pause the video, try it yourself, and then unpause to make sure that you've got an understanding of what's happening. And we're back. So I'll take the process here and equate the functions. That's step 1. I notice here that this is a quadratic, so I'm going to make one side 0. Okay, I'll try and factor this. Oh no, it doesn't factor well. Okay, that's fine. I'll go to the quadratic formula. The quadratic formula. 2 squared is 4, minus 4 by a, which is 1, by c, which is 7. All over 2a, all over 2a. Okay, let's check out what happens here. So I'd have negative 2 plus or minus the square root of 4 minus 28, so negative 24, all over 2. Okay. Oh no. Look at this. No. That's not okay. Okay, not a real number. So this equation that we tried to solve over here has no real solutions. What does that mean about these two functions? If the equation that happens when you equate them has no real solutions, then these functions have no points of intersection. Or in other words, you could say they don't meet. Now you could also check that out on your GDC. There are the two functions. Let's graph them. I don't see a lot of them. Maybe I'll change up my axes here. I could just zoom out. So I zoom out on these functions. I see that they actually don't meet, and that confirms what we found algebraically. Another way that you could have checked this, though, is right at this stage, you could have used the discriminant and maybe saved yourself a little bit of trouble by saying, let's find out if this has solutions, and then if it does, well, then I'll go ahead and solve it. Otherwise, I'll just tap out. Now, I kind of think finding the discriminant every time is a bit of overkill, because it's not that hard to throw this stuff in the quadratic formula. But as soon as we find a negative discriminant, there are no solutions, which means no points of intersection, and they don't meet. So let's tweak this question a little bit. I've got the same quadratic here. I'm just wondering, for what values can I actually make them meet? So I'm going to take this same sort of quadratic, the exact same quadratic, the exact same kind of line, one with a slope of 1, and some random y-intercept. And when are they going to meet? So as soon as you have one of these ones where it says that they meet, or how many solutions they have, or how many points of intersection, then we might be thinking about a discriminant question. You can do this in a bunch of steps. A meeting place would make me think of this. X squared plus 3x plus 10 equals x plus k. Okay. I might move some stuff over, so I'll get plus 2x plus 10 minus k equals 0. I mean, to solve that, we'd find our meeting places. If they meet, then this must have at least one solution. Well, what does that mean for the discriminant? If it has at least one solution, that means the discriminant is either 0, which means there's one solution, or the discriminant's positive, which means that there's two solutions. I wonder if there's a mathematical symbol that means that, either equal to or greater than. Oh my gosh, there is. If they meet, then the discriminant must be 0 or greater. So there's a fair bit of problem solving that's happening here. There's a meeting point, so you set them equal to each other. It tells you the number of solutions, at least one. So you know you're talking about discriminant. And that discriminant can either be 0 or positive, which means that it could be greater than or equal to 0. Now we're kind of ready to get into the meat of solving the problem. And from here on in, it will be sort of algorithmic. But up to this point, it's been a lot of abstract thinking. So b squared minus 4ac is greater than or equal to 0. Let's check that out. So that's 2 squared minus 4 by a. Hey, I wonder what c is. So a is 1. B is 2. C is this whole mess of constants at the end. C is 10 minus k. Whatever the constants are at the end. Now the algebra will take care of itself. It's a question of making sure that we set it up properly. And at the end, we'll pick some k value and check that it actually works. So 4 minus, let's see, 4 by 10 minus k is greater than or equal to 0. Let's keep this going. 4 minus 40 plus 4k is greater than or equal to 0. Okay, so that's negative 36 plus 4k is greater than or equal to 0. 4k is greater than or equal to 36. K must be greater than or equal to 9. I wonder if it's true. Let me put in 9, which is right on the boundary. At 9, there should be one point of intersection. So I've got that original quadratic in there. I'm going to change this linear to x plus 9. Oh my gosh, they do appear to have one point of intersection. It said k is greater than or equal to 9, so what if I put in 10? Will they meet? Yeah, they'll have 2 points of intersection. If I put in 11, they'll still have 2 points of intersection. Now you might say, hold on, this is lying to us. At some point, what if we put in 100? Ha! See, Toms? They don't meet. But do they? Let's check out our window settings. Let's go to a y max of, I don't know, 120. So that we see more. Oh, they do meet, right? They just meet high up. And they're always going to meet. The higher you put that x-intercept on the linear function, they're definitely going to have 2 points of intersection. So for all values of 9 or greater, you're going to have at least one point of intersection between these two functions. In terms of practice material, I'm recommending 42 to 44, number 1 AC, that's analytic techniques, 2 AC, that's GDC techniques, and number 7. You can also try other ones on that page, though they do talk a lot about tangents, which is something that we'll probably put off talking much about until we hit calculus. The other thing to make sure that you do is submit your quadratics assignment. Good luck with the material, folks. Take care and have a great break.